Okay, this is velocity and acceleration of center of mass. This is where things get a little bit more challenging, okay? Last year we learned a little bit about the center of mass and how it moves. Now you're going to learn a little bit more in depth about it. The velocity of the center of mass is simply the rate at which the center of mass position changes. Okay, so if the center of mass can move, okay, and this is the rate at which that position changes. Okay, so I'm just going to walk you through each of the steps of this derivation here. It's already spelled out for you, but we just need to explain what's going on here. This right here is the center of mass equation for position. Okay. So what I'm going to do here is I'm going to take, if this is the position equation, I can take the derivative, okay, to get velocity. Okay. Okay, great. Now that I've taken the derivative, you should notice, okay, that 1 over m is a constant, so we can factor that out. So I'm going to say to factor a multiplied, okay, constant out of derivative. Okay. Okay. For the next part, okay, what I'm going to do is, well, you should understand that the derivative of a sum is the same thing as taking the sum of the derivatives, okay? So derivative of sum is the same as the sum of the derivatives. That's all I'm doing here, okay? You should also recognize that m sub I, okay, m sub I is a constant, okay? And we're not integrating with respect to it, so we can factor it out. Okay? And the final step here is that you should recognize that you ultimately end up with dx sub I over dt, which would be equal to v sub I of that one object. Okay? So that's just the derivation for it, right? You can see that how we get this right here. You're doing mass times velocity instead of mass times position now. So that should make sense, right? This is more so, I mean, that's kind of more generalized, right? Okay. A couple of other things to go over is that there's a relationship between center of mass velocity and the momentum of the system. We touched on this very briefly in Physics 1, okay? The velocity of the center of mass is equal to the net momentum, okay, over the total mass. Okay? So that becomes P equals mv, okay? And you can see that P net would be equal to the mass total times the velocity of the center of mass, okay? That's one way to relate, those, okay? What about for the center of mass's acceleration, okay? Well, if we know, right, it's going to be very similar. If we take the derivative of that previous equation where we got the center of mass velocity, we're just going to end up getting, and no point in going through all the steps because we're just going to end up getting m sub I times a sub I over m, which is total mass. Okay, wait a minute, m times a is just the force, right? So really, the acceleration of the center of mass is equal to the net of all forces on all objects, okay, all over the total mass, okay? And that should make sense, right? It's F over M, right? That should make sense, okay? And the relationship between the center of mass acceleration and the total force on the system, right, is that the F net on the whole system, okay, should be equal to the total mass times the acceleration of the center of mass, okay? So we're just writing some equations here that show these relationships between, different motions of the center of mass, okay? Okay, internal force is simply, so external forces are where the agent, okay, which is what's doing the forcing, doing the forcing, okay, is in the same system as the object, okay, which is being forced, okay? The external force, an external force is where the agent is outside the system, okay? Is outside the system. I guess I should say that object is included in, okay? So there you go, right? Internal forces, external forces. Now we can see that there's a bunch of objects, right? Each object that is high above, so these are objects above the Earth, they all have gravitational forces that are acting upon each other. Earth is also exerting gravitational force on each of these three objects, okay? So let's figure out what's internal, external, okay? Internal to the system. Okay, well, if a system is A, B, and C, then it's going to be anything that A, B, and C do to each other. So that's going to be that F of A on B is equal to negative F B on A. And that is just Newton's third law, right? Okay. F of A on C is going to be equal to the F of C on A. Okay. And then we should also see that F of B on C is going, oh, sorry, negative FCA. And this should be negative F C on B. Okay. Anything that's external is going to be anything that has the Earth in it. Okay. Anything with Earth in it. Okay. The Earth is all external. Now, let me kind of show you why that is. Okay. Why is it that this is all? Why is it all? Why are they? Or sorry. Why are they all? Why is Earth external? Right. Well, let me show you. Okay. If we take, for example, okay, F net, and we set it equal to, F net, if I add up all of the force vectors, then you should see F, A, B, plus, I guess F, B, A, plus F, A, C, plus F, C, A, plus F, B, C, plus F, C, B. Okay, let's see, we've got that. And then we need to add in the Earth, or the Earth acting on it. Sorry, that should be F, E on A, F, E on B, F, E on C. Okay, and what you should notice is we said that the same letters, right? AB is the negative, or sorry, AB is equal to negative BA, right? AC is equal to negative CA, and so on and so forth. So you notice that all of these are actually going to end up canceling each other out. Okay. Okay. And that's all you got to do. And then you're just left with that final expression right here. Okay. Which is that. Okay. That's all you got to do. Okay. All right. That's that section. We'll move on to the next one here in a little bit.